Okay, let's move on to some of the actual physiology of respiration. I think we recognize that as we breathe in, our chest cavity expands, and then as we breathe out, it contracts. So basically, air is moving into our lungs when the pressure inside is less than atmospheric pressure, and that is what is happening when our chest cavity expands. That expansion of volume causes a lower amount of pressure inside, which then allows air to be drawn into our lungs. Similarly, when we breathe out, our chest cavity compresses, forcing air out. Again, I think it's very more intuitive to us than kind of thinking about in these scientific terms, but really what we're talking about is the atmospheric pressure and the change in that atmospheric pressure from inside that chest cavity compared to the outside environment. And this holds with something called Boyle's law, which says as the size of a closed container decreases, the pressure inside increases. So again, as your chest cavity gets smaller, the pressure increases and you breathe out. And that's what this image here is showing you. You can see this piston pushing down on these fluids and, particles. And as that volume decreases, the pressure proportionally increases. Okay, so a few little definitions for you. So quiet inspiration, basically that is just you sitting there, you're not exerting any kind of major effort. It's just your normal everyday inspiration is considered quiet inspiration, breathing in. When that happens, your diaphragm will move only a small amount, 1 centimeter, and your ribs are going to be lifted by your external intercostal muscles. Again, the pressure will decrease and you breathe in. Quiet expiration, again, that's just your normal everyday breathing out. It's passive, so no muscles are helping you breathe out, again, during rest or quiet expiration. Rather, it's simply the relaxation of the diaphragm and the external intercostals that decreases the chest cavity. Again, by decreasing that volume, it increases the pressure and air moves out of your lungs. Okay, but what about labored breathing, or when, let's say, you've been running or exerting some, physical exercise? So that's considered forced instead of quiet. So it's forced inspiration and forced expiration. And some other muscles are also going to get involved. So for breathing in, not only is it your external intercostals and your diaphragm, but now that sternocleidomastoid, that muscle sort of in your neck area, scalenes, pectoralis minor, and so you can see scalenes right here. Pectoralis minor is not shown in the image. They're also going to help lift your chest up as you gasp for air. I mean, think about it when you see someone really panting after having run, you see their neck is even kind of, the muscles in the neck are even bulging out. That's that sternocleidomastoid that's helping lift up the chest cavity. And then with forced expiration, the abdominal muscles are also contracting to help force air out. As well as the internal intercostals are also depressing your ribs, again, forcing air out. Sometimes you may even see people bent over, kind of help pushing air out during labored breathing. So this cycle is just your summary. You can, this is just a summary of those two slides. So again, during normal quiet inhalation, diaphragm, external intercostals are contracting. If it's labored, like after you've been running, the sternocleidomastoid, the scalenes, pectoralis minor are also helping you. Regardless of which one of those processes being used, the thoracic cavity increases and the volume of lungs expands. That means the pressure decreases, which means you breathe in air. And then as you exhale, again, depending on whether it's just the normal quiet exhalation, so the diaphragm and external intercostal simply relaxing, or during forceful exhalation where the abdominals and internal intercostals muscles are also helping contract that thoracic cavity, decreasing its volume, increasing the pressure, and allowing you to breathe out. And then obviously that's a circle of a process. All right, so how do we actually measure lung volumes and capacities? The tool we use is called a spirometer. Sometimes it's also called a respirometer. And then the graph that's produced is called a spirogram. So here's another definition for you. So a minute volume of respiration is simply the total volume of air taken in during 1 minute. So it's something called the tidal volume, which we'll see in a second, times the number of breaths per minute. So assuming you take 12 breaths per minute with a tidal volume of 500 milliliters per breath, you just multiply the two, and then you get your minute volume of respiration. So let's take a look at a spirogram. So in here are some more of your definitions, and this is just a graphical representation of all of those. So your tidal volume is the amount of air that moves in or out of your lungs with each respiratory cycle. So one breath in and out is your tidal volume, and that's these middle like little waves here. And here's the start of the record. So it would start here, 1 breath in, 1 breath out. That's 1 tidal volume. Then your inspiratory reserve volume, right here, is the extra amount of air that can be inspired with maximal effort after reaching the end of a normal quiet inspiration. So again, if we go from here, we have a normal inspiration in, out, in, and then all that extra that you could possibly breathe in. That's your inspiratory reserve volume. And then going the opposite direction, the expiratory reserve volume, this amount right here, that's the amount that you can breathe out after a normal breath out. So again, as you breathe out, like a normal breath out, and then you would try to breathe all the extra out until you can't breathe out anymore. There is something called a residual volume. That's the amount of air that no matter how hard you try, you can't possibly get out of your lungs or your trachea, because your trachea also doesn't totally collapse. So no matter how hard you breathe out, there's always some small amount of air that will remain in your respiratory tract. A few other definitions. Inspiratory capacity right here. This is the maximum amount of air that can be taken in after reaching the end of a normal quiet expiration. So we breathe out normally, and then we take 1 giant lungful of air. Mathematically, it's simply the tidal volume plus the inspiratory reserve. There's something called the functional residual capacity. So that's the amount of air remaining in the lungs after a normal passive exhalation. So that's just this. That's just the expiratory reserve plus the residual volume. And then there's something called vital capacity. That's the maximum amount of air a person can expel from lungs after a maximum inhalation. So the biggest breath in and the biggest breath out that you can take, that is your vital capacity. And then you simply add the residual volume to that, and you get your total lung capacity. So what is the composition of air versus alveolar air versus the air that you breathe out? So again, the air in the atmosphere versus alveolar air versus expired air. So, and these are rough numbers, rounded up. Air, the air we breathe in general, is 21% oxygen. Vast majority of it is nitrogen, actually, and very little of it is actually carbon dioxide. If we were to sample the air in your alveoli, there's less oxygen. You'll notice that the nitrogen levels are the same, and then there's a lot more carbon dioxide. Now, that's probably not surprising. We expect there to be more carbon dioxide, right, as there's gas exchange, and then we expect there to be less oxygen, again, as gas exchange occurs, and blood is picking up oxygen and delivering carbon dioxide to our lungs. Nitrogen very rarely goes into solution. It does not, has very little affinity for liquids, so like our blood or plasma, and we'll talk a little bit about this in a little bit about nitrogen will go into solution, but only under great pressures, like if you were diving deep underwater. Now, if we were then to sample the air that you breathe out, you'll notice that actually, while still lower in oxygen than the atmospheric air, it is higher in oxygen than the alveolar air, as well as lower in carbon dioxide than alveolar air. So here's just a quick thought question for you. So how come the alveolar air has less oxygen than atmospheric air? I already mentioned that a moment ago. But how come expired air has more oxygen than alveolar air? What do you think is going on? All right, I'll give you guys a minute to think about that. Maybe not a literal minute, but so think about this. As you're breathing in air, right, there's a 21% oxygen. You have the gas exchange that's occurring. Now, some of that air that you just breathed in, some of that is staying in the trachea. Not all of it makes it to your lungs, right? So as you breathe out, some of this oxygen, some of this air that you're breathing out is going to mix with that air in your trachea where gas exchange has not occurred. So there's that mixing of, I'll say it this way, like, maximum oxygen in air versus the lower amount that's in the alveoli. And that's how we get a slightly higher amount of oxygen in expired air due to that mixing than we see in the alveolus. A few bits of terminology for you. You may have heard the term compliance. That's simply how easy the lungs and chest wall expand. So if the saying is, I shouldn't say this, this terminology is if your lungs are compliant or show large compliance, that means it's very easy for you to breathe and expand your chest cavity. When you hear something like there's low compliance in the lungs, it's very difficult for an individual to breathe. Eupnea is simply normal breathing rate and depth, so you're not breathing shallow or particularly deep or rapid or slow. Apnea is where you would hold your breath, so you may have heard of sleep apnea where people suddenly just stop breathing. There's dyspnea, it's where there's painful or difficulty breathing, and then tachypnea is where you have a rapid breathing rate. Now, you may have a rapid breathing rate because you've just ran a mile, or more concerning is if you have a rapid breathing rate and you're just sitting there in front of a computer minding your own business, right? Maybe like you might see that like if someone's having possibly a panic attack or something like that. But anyway, tachypnea is simply a rapid breathing rate. All right. Hopefully all of that makes sense to you. The next section will be pretty short and related to our breathing.